Let's start our complex analysis. This is our lecture 1, complex analysis. And in today's class, we will start from the Cauchy-Riemann equations. The Cauchy-Riemann equations. Okay. So, before starting this, you make sure that you know the fundamental things of complex numbers and what is limits, continuities, limit, continuity and differentiability. Okay. So after knowing this, or if you know this thing, then you can come to this Cauchy-Riemann equation. Now I will start here, and I am making sure that you know these things. Basic fundamental things of complex number, then limits, continuities and differentiability. So now comes to Cauchy-Riemann equation. Now first I will give a statement of a theorem and I will prove it. Okay. So this is the statement of this Cauchy-Riemann equations. So let f of z equal to, let your f of z is equal to u of xy plus I times v of xy be differentiable at a point, be differentiable at a point z naught equal to x naught plus I y naught. Okay. Then uxy and vxy, then uxy and vxy have first order partial derivatives, have first order partial derivatives, ux at x naught y naught, uy at x naught y naught, vx at x naught y naught and vy at x naught y naught. At this point x naught y naught, the first order partial derivatives of u and v are these things, and these partial derivatives satisfy, and these partial derivatives satisfies Cauchy-Riemann equations. Satisfies Cauchy-Riemann equations given by Cauchy-Riemann equation, or shortly you can say this is C-REquations given by ux at x naught y naught is equal to ux is equal to vy, ux is equal to vy at x naught y naught, and uy at x naught y naught is equal to minus vx at x naught y naught. Also f dash z naught is equal to ux at x naught y naught plus I times vx at x naught y naught, and this thing also since here ux equal to vy, so I can add this is vy at x naught y naught, and your vx x naught y naught, vx is your minus uy, so I can add this is minus I times uy at x naught y naught. Okay, so this is the statement and we have to prove this thing. So Now, what is the given condition? Given that f of z, which is your u of xy plus I times v of xy, this is differentiable at this point z naught. So, given that f of z, given that f of z, which is your u xy plus I times v xy, this is differentiable. This is differentiable at z naught. Z naught means this is your x naught comma y naught, and this is x naught plus I y naught. So if this f of z is differentiable at z naught, then you can say, then we can say that f dash z naught exists. So what do I mean by f dash z naught exists? That means limit z tends to, or limit h tends to 0, limit h tends to 0, f of z naught plus h minus f of z naught divided by h exists. This is the value of f dash z naught. F dash z naught means this is nothing, this is the limit z, limit h goes to 0, f of z naught plus h minus f of z naught divided by h. So if f dash z naught exists, that means limit h tends to 0, this function exists. So if this thing exists, so we can say hence the limit is independent of path in which h approaches to 0. Hence the limit exists. Hence the limit is independent of the path in which h approaches to 0. In which h approaches to 0. Because since s goes to 0 and this is a complex analysis, this you know from the real analysis, when if I will say limit x goes to 0 in real analysis, since this is one dimension, uh, suppose this is one dimension and this is 0, then limit s goes to 0 means you have to see only the left hand limit and right hand limit, and in left hand limit you are showing this limit x goes to 0 minus, and in right hand limit you are showing limit h goes to 0 plus. So if this left hand limit and right hand limit are equal, then you can say that limit h goes to 0, and that value is equal to limit h goes to 0. So h goes to 0 in real analysis means you have to just find what is the left hand limit and what is the right hand limit as x goes to 0. But in complex analysis, suppose complex analysis C is equivalent to your R2. That means this is like your x-axis or real axis, and this is your y-axis, or you can say this is your imaginary axis. So if I will say limit s goes to 0, this is your 0, and s goes to 0 means you can approach to this 0 in various ways, like this is from the negative real axis, or this is from the positive real axis, or this is from positive imaginary axis, or this is from negative imaginary axis. Also you can approach this thing from this way, this way, this way, this way, in different ways. There are different ways, and this is saying this, yes, a limit s goes to 0, this thing exists. That means uh, hence the limit is independent of the path in which h approaches to 0. So in which way we will approach, this thing does not matter. Okay, since limit exists means in there are several ways. So in which way you will approach, this thing does not matter, but in every way if you will approach, or in any way if you will approach to this s goes to 0, this thing exists means this thing is a particular finite quantity. Okay, if you will go in this way, this thing also gave you uh, a same value, and if you will go in this way, this will give you same value. It means this is independent of path. In which path you are choosing, that thing doesn't matter, but the limit is finite. Okay, so now next what we will do. So limit h goes to 0 and all things are complex number. So let h is equal to h1 plus I s2. So if your h is h1 plus I s2, now consider what is your f of z naught plus s minus f of z naught divided by h. So what is this thing? F of z naught plus s minus f of z naught, and your f of z is u of xy plus I times v of xy. So f of z naught plus s. If your h is h1 plus I s2, so f of z naught plus h is your u of x naught plus h1 comma y naught plus s2 plus I times v of x naught plus h1 comma y naught plus s2. In place of f of z naught plus s, I can add this thing. Similarly, in place of f of z naught, I can write this is u of x naught comma y naught plus I v of x naught comma y naught divided by h. So I can arrange this thing also by combining. So this is u of x naught plus h, u of x naught plus h comma x naught plus h1 comma y naught plus s2 minus u of x naught comma y naught plus I times this one and this one. So I times this is v of x naught plus h1 comma y naught plus s2 minus v of x naught comma y naught divided by h. H or in place of h, I can add h1 plus is2 because h is Java. This okay. So then I can write this is u of x naught plus h1 comma y naught plus s2 minus u of x naught comma y naught divided by this is h1 plus is2 plus I times, then this is v of x naught plus h1 comma y naught plus s2 minus v of x naught y naught divided by h1 plus is2. Okay, so the f of z naught plus s minus f of z naught divided by s value is this much. Now I will come, suppose s goes to 0 along real axis. So we have to, it is given that limit s goes to 0, this thing exists. Now I got what is this much. Now I will apply limit s goes to 0 in two ways. Like this is your real axis. So if I will approach it via real axis like in this way, or if I will approach via imaginary axis, this is my imaginary axis. So this is the positive imaginary axis, this is the negative imaginary axis. So if I will approach via real axis or if I will approach via imaginary axis, then what happens? Then I will say, suppose s goes to 0, suppose h goes to 0 along the real axis. So if s goes to 0 along real axis, so that our h will be only h1, because in real axis you know h is your h1 plus is2. So in real axis your imaginary part is 0, that means your h2 is 0. So h will be only h1. Okay. So if I will approach along real axis, so h will be your h1. Then what will be our f dash z naught? F dash z naught is your limit s goes to 0 of f of z0 plus h minus f of z0 divided by h, and this is your limit. In place of h, this is h1, so limit h1 goes to 0, and what is f of z0 plus h minus f of z0 divided by h? This is your this one. I just simplified this one as your this one, so you just write this thing. So h1 goes to 0, you write this thing. So this is u of x0 plus h1 plus y, sorry, u of x0 plus h1 comma y0, because here h2 is 0, h2 is 0, so in place of h2 I will put 0. So u of x0 plus h1 minus u of x0 comma y0 divided by h1 plus I times, again this limit h1 tends to 0 of this one. So what is that one? This is your u of, sorry, v of x0 plus h1 comma y0 minus v of x0 y0 divided by h1, and this is your limit h1 goes to 0 of, sorry, limit h1 goes to 0, so limit h1 goes to 0. What is limit in this, limit of this value? This is your ux of x0 y0. Similarly, this is your I times vx x0 comma y0. So this is your f dash z0 is this one. This is your equation 1. Similarly, suppose h goes to 0 along the imaginary axis. Along the imaginary axis, so that our h will be is2, because from the imaginary axis the real part is 0, so h1 will be 0, so your h will be only is2. Then what we will write? Then our f dash z0, this is your limit h goes to 0 of, which is your f of z0 plus h minus f of z0 divided by h. So this thing can be written as limit is2 tends to 0, and what is f of z0 plus h divided by f, this thing, this value is this much, so you just put that thing here. Okay, so this will be u of, and in place of h1 you will put 0 also. Okay, so f of, sorry, u of x0 comma y0 plus s2 minus u of x0 y0 divided by ih2. The h1 is 0 plus I times limit is2 tends to 0 of, then put this value where h1 equal to 0, so this will be v of x0 comma y0 plus s2 minus v of x0 y0 divided by is2. Okay, so this will be this much. Now simplify this thing. So limit is2 tends to 0 means limit h2 tends to 0. Okay, so what will be this one? So limit h2 tends to 0 of, You just write what is written here. Taking 1 by I to outside, then this will be u of x naught comma y naught plus s2 minus u of x naught y naught divided by s2, and this is this I is here and this I is here, so I divided by I, this will be 1, then limit h2 goes to 0 of this is v of x naught y naught plus s2 minus v of x naught y naught divided by s2. So 1 by I taking outside, and the limit of this thing is nothing but this is vy at x naught y naught. Similarly, here I by I can cancel out, and this will be vy vy at x naught comma y naught. Okay, and this 1 by y, sorry, this is uy. First one is here uy. So this is u of this thing. Okay, so this is uy of this thing, and 1 by I. So first I will write this real part. So this is your vy at x naught y naught, and this is 1 by I. If I will multiply I on both numerator and denominator, 1 by I, which can be written as I divided by I square, and this is your minus I. Okay, so in place of 1 by I will write minus I. So alright, this is minus I of uy x naught y naught. This is your equation 2. So your f dash z naught is this one, and your f dash z naught is this one. So both so by comparing this equation 1 and 2, comparing equation 1 and 2, what we will get, the real part will be equal to real part and imaginary part will be equal to imaginary part, because the left hand side is same f dash z naught. So what we will write, that ux is equal to vy or ux at x naught y naught. You can say this is your ux at x naught y naught is equal to vy at x naught y naught, and uy at x naught y naught is equal to minus vx at x naught y naught. So this is the proof. Okay, this thing it is given to proof, and this is f dash z naught equal to this one, and this thing is also you got, and this is also part of that proof. Okay, now this thing is completed. Now come to a problem. Suppose f of z, let f of z is given z bar. So z bar means your z is f of, we know always our z is x plus iy. So what will be your z bar? This is your x minus iy. So your f of z is z bar, that means your x minus iy. So what is the real part here? U of xy. So this thing can be written as u of xy plus I times v of xy, where u of xy is the real part of f of z and v of xy is the imaginary part of f of z. So your u of xy is x and v of xy is your minus y. So now find what is your ux. Ux is your 1 and uy equal to 0. Similarly, vx, v is this one, so what is vx is 0 and vy is minus 1. So if you check the Cauchy-Riemann equation, and you know your Cauchy-Riemann equations are, what is Cauchy-Riemann equations? Cauchy-Riemann equations are ux equal to vy and your uy equal to minus dx. What we proved in the above theorem. Okay, so this is the Cauchy-Riemann equation. So if you will check here, ux is not equal to vy because ux is 1 and vy equal to minus 1. So since ux is not equal to vy, so CR equations are not satisfying. CR equations are not satisfying. Okay, CR equations are not satisfying. Thus, by the above theorem, you can say f of z, which is z bar, is not differentiable. Is not differentiable. It's not differentiable at any point. At any point except 0. Because at origin it is differentiable, because at origin here both x and y are 0, so your ux will be 0, uy will be 0, vx will be 0 and vy will be 0. So this is not differentiable except at 0. So what we got here, so okay, let's come to another example. So CR equations is not satisfying, that means it is not differentiable. That means what we got here, if CR equation is not satisfying, if CR equations are not satisfying, implies function is not differentiable. That means function is not differentiable. Okay. So there is a question mark. There is a question mark. If CR equations are satisfied, or if CR equations are satisfying, is that function is different? If CR equation is satisfying at a point z, is that function is differentiable at z? So if a CR equation is satisfying, is that differentiable? But the question is no. In general, it is no. Okay. So now comes to an example which satisfies the CR equation, but it is not differentiable. So now coming to an example, let f of z is equal to xy divided by x square plus y square, z not equal to 0, and this is 0 if z is equal to 0. Okay, so if f of z is giving this thing, so whether we have to check whether it is differentiable at 0 or not. Check if 0 exists or not. So at this point 0, first we will check whether the CR equations are satisfying or not. So now f of z is this thing. So what is your u of xy and what are your v of xy you have to write. So your u of xy means your real part. So this is xy divided by x square plus y square if z not equal to 0, and this is 0 if z is equal to 0, and your v of xy, this is 0 for all z. Okay, for all z your v of xy is 0. Calculate what is my ux at 0 0. You know the formula for ux at 0 0. This is your limit goes to 0 of u of 0 plus s comma 0 minus u of 0 0 divided by h. So which is limit s to 0 of u of h minus u of 0 0 divided by h. So this is limit s goes to 0 of u of h 0. sorry, for h non-zero, this is the value of u of xy. So u of xy is this one. So for u of h0, you just put in place of x, it is 0. Sorry, in place of x, you have to put h, and in place of y, you have to put 0. So if you will put this thing, it will be 0. You will get, and u of 0, 0 is 0. So this is 0 minus 0 by h. 0 minus 0 is 0 by h. So of 0 by h is 0. Similarly, if you will evaluate what is uy at 0, 0, then this will be limit s goes to 0 of u of 0, 0, 0 plus h, or you can say this is, suppose this is k goes to 0, so u of 0, 0 plus k minus u of 0, 0 divided by k. So this will be limit k goes to 0 of u of 0 minus u of 0, 0 divided by k. So if you will see this thing, so u of 0k, in place of x you will put 0, in place of y you will put k. So it will be 0. Then u of 0, 0 is 0. So this is 0 minus 0 by k. So this is limit k goes to 0 of 0 by k. So 0 by k is 0. So this is 0. And your v of xy is 0. So if you will take the partial derivative with respect to x, it will be 0. Again vy will be 0. So if you will see, you will get here ux at 0 equal to vy and uy at 0, 0 equal to minus vx at 0, 0. So you can say your CR equations are satisfying. So CR equations are satisfying. So if the CR equations are satisfying, if you will check whether f dash z not f dash at 0 exist or not. That means f is differentiable at 0 or not. So before going to this differentiability, first you just check whether, now to check whether f of z is continuous at 0 or not. Is continuous at 0 or not. So how to check the continuity? That means to check that limit z goes to 0, f of z is your f of 0 or not. So if this thing satisfying, then you can say this is continuous at 0. So now evaluate limit z goes to f of z. So this is limit z goes to 0 means your z is x plus iy. So this is x plus iy goes to 0, and your f of z is xy divided by x square plus y square, and xy goes to 0 or z goes to 0 means you can approach in this way. Let y equal to mx. So when x goes to 0, at that time y goes to 0, that means you can say z goes to 0. Okay, so I can write this thing, limit x goes to 0, and I am taking this y equal to mx. So in place of x it is x, in place of y it is mx. Then x square divided by mx plus x square, then limit x goes to 0. So from both numerator and denominator, x square can cancel out, then only left is m divided by 1 plus m square. So this will be m divided by 1 plus m square. So which is different for different values of m, which is different for different values of m. Okay, so if this is different for different values of m, we know if limit is a particular quantity, or this is a finite quantity, then you can say the limit exists. But it is saying that it is different for different values of, so limit is always unique. So you can say a limit z goes to 0 does not exist. Okay, so if this thing does not exist, and here f of 0 is 0, it is given in the above question. Okay, so it is given in the above question that when z is equal to 0, when z is equal to 0, f of 0 is 0. So but this one, this thing does not exist, so f of z is not continuous. This thing is at z equal to 0. So since it is not continuous, not differentiable. This is not differentiable at z is equal to 0. If something is not continuous, then how can you say it's differentiability? Because if it is continuous, then you can check for its differentiability. Okay, so since it is not continuous, it is not differentiability. So what we got here, it satisfies. Okay, this thing completed. So what is the sufficient condition, or what is the sufficient condition for differentiability? Is the sufficient condition for differentiability, because we know already if something is satisfying C-R-equations, this thing does not imply that it is continuous. Sorry, it does not imply that it is differentiable. So there are some things which are called sufficient conditions. So if you will add some more conditions here, then it will be a sufficient condition for differentiability. So what is the sufficient condition? Okay, so now we will see a theorem which gives you a sufficient condition for the differentiability. Okay, so now comes to that theorem that f of z is equal to, that is the sufficient condition. Sufficient condition for differentiability. This theorem. Okay, so let f of z, let f of z is your u of xy plus I times v of xy be a function defined in a region D, be a function defined in a region D, be a function defined in a region D such that u, v and their first order partial derivatives, such that u, v and their first order partial derivatives and their first order partial derivatives, u, v and their first order partial derivatives are continuous in D. Okay, if the first order partial derivatives of u and v, if the first order partial derivatives, if the first order partial derivatives, if the first order partial derivatives of u and v satisfies the Cauchy-Riemann equations, satisfy the CR equations at a point xy, at a point z, at a point xy belongs to that region D, then f is differentiable at z. Then f is differentiable z. That means f is differentiable at xy. So what is the statement is saying? If f of z, which is your u of xy plus I times v of xy, be a differentiable function defined in a region D. Okay, so in a region D, this is saying that this f of z is defined such that u, v on their first order partial derivatives. So what are the first order partial derivatives? Like your us, uy, vx, vy. So these things are continuous in D. Okay. So if the first order partial derivatives are of u and v satisfy C-REquations at a point xy belongs to D, then f is said to be differentiable at that point xy. Okay, now we'll prove it. So given that f of z is defined in a region D, and then it is saying that the first order partial derivatives of u and v are continuous at xy. Okay, the first order partial derivatives of u and v are continuous in D. It means this is continuous at any point xy. So first I will write, since u of xy, v of xy, and their first order partial derivatives, their first order partial derivatives u and v and their first order partial derivatives are continuous in D, and let z, which is your point xy or x plus iy, you can say, this thing belongs to D, be arbitrary. So here u of xy, v of xy and their first order partial derivatives are also continuous at this point xy. So if these things are continuous at xy, then by using the mean value theorem of two variables, and then by using the mean value theorem, for mean value theorem of two variables, we have u x plus x1 comma y plus x2 minus u of xy. This thing can be written as h1 ux at xy, s2 vx, sorry, s2 s2 at xy plus h1 epsilon 1 plus s2 epsilon 2. This thing by using this mean value theorem for two variables which you studied in your multivariable calculus. So u of x plus h1 comma y plus s2 minus u of xy is your h1 into ux at xy plus s2 into uy at xy, h1 epsilon 1 plus s2 epsilon 1. Okay, let that be this be equation 1, and where epsilon 1 epsilon 2 tends to 0 as h1 and s2 tends to 0. Okay, similarly for v we can write v of x plus h1 comma y plus s minus v of xy is equal to your h1 vx at xy plus s2 vy plus h1 epsilon 3 plus s2 epsilon 4. This is your equation 2, where this epsilon 3 and epsilon 4 as h1 s2 tends to 0. Okay, let this be your equation 2, and let h is your h1 plus I s2. Okay, so now consider our f of z plus h minus f of z divided by h. So if I will consider this one, this is your 1 by h, and what is your f of z plus h minus f of z? This is your u of x plus h1 comma y plus s2 plus v of x plus h1 comma y plus s2 plus this is I times, okay, this one minus this is u of x comma y plus I times v of x comma y. Okay, so this is your 1 by h. Now combining real part with real part and imaginary part with imaginary part, so what we will get, this will be your u of x plus h1 comma y plus s2 minus u of xy plus I times this is v of x plus h1 comma y plus s2 minus, I'm taking I common here, okay, so v times v of xy, and this will be 1 by h of, and what is this one, already in equation 1 this value is given to you, so now put that value, this will be your h1 of ux at xy plus s2 of uy at xy plus h1 epsilon 1 plus s2 epsilon 2. Similarly plus I times, now put this value from equation 2, so this will be h1 v at xy plus vy at xy plus h1 epsilon 3 plus s2 epsilon 4. Okay, so this is that much. Then now combining real part with real part and imaginary part with imaginary part, so this is h1 u x at xy and this is h1, this is I times vx, okay, this is h1 I times vx. Similarly this is the term containing s2, similarly this is the term containing s2, and this is the term containing epsilon 1, and this is the term containing, sorry, this is again a term containing h1 with epsilon 1, this is h1 with epsilon 3, and this is again s2 with epsilon 2, this is s2 with epsilon 4. So now combining these things, 1 by h whole into h1 of, okay, this h1 of this is 1 by h whole into h1 of this is u, this is I times h1 of this I times, and h1 we already took common, I times this is vx x, this is h1 into this one. Similarly s2 whole into this is uy, this is y at xy, and this is s2 is here and I is there, so I times v xy, then h1 epsilon 1, then h1 taking common, this is epsilon 3 epsilon 1, and then I times I, similarly taking s2 common, this is your this I is epsilon 4. So what you got here, this is 1 by h whole into, this is h1 ux of this one, and this is is2 of ux. Okay, so now I will use the CR equations. So if I will put CR equations, then what I will write? So if I will use CR equations, you know your CR equation, your ux equal to vy and uy is your minus vx. Ux is vy and uy is your minus x. Now I want to write this thing in terms of u only. Okay, so if there is vy or if there is minus vx, I will replace this thing by ux or uy, whatever it may be. Okay, so now I will write this is h1 times this ux of ux at xy, and in place of vx and your vx uy is minus v, so vx is your minus uy, so I will write minus uy. Okay. These things are not working. Leave this thing. So in place of vx, I will put minus uy. So this is minus, and this is uy at xy, then plus s2 up, and this is uy at xy, and in place of vy, what I will write? Vy is your ux. So I will write this is I times this is ux xy, then h1 times this is epsilon 1 plus I epsilon 3 plus s2 times epsilon 2 plus I epsilon 4. Now 1 by is, then this is h1 ux xy, and this is I h2 uxy, so I can write this is h1 plus I h2 of ux at xy. Okay, then this is h1 whole into minus uy at xy, and this is s2 uy xy. So what I can write here, uh, um, so if I will write in place of uy, sorry, one I is there. Okay, in place of vx I just put uy, but I is there. Okay, I just missed that one. So I will take minus y common. So this is minus I is there. So if I will take minus I common from uy, combining this uy term. Okay, so if I will take minus I common, then h1 minus I common, then this is h1, and this is simply s2, and you know simply s2 means this is 1 times s2, so your 1 is minus I square. Okay, 1 means this is minus, and so I can put minus I square. So if I will take minus I common from minus I square, so the only thing left will be plus I, so this will be h plus I times s2. Okay, so in place of plus 1, it is written minus I square. Okay, so if I will take minus I common, then it will be only I, then s2 is here, and then your uy at xy. Then whatever left, h1 times this is epsilon 1 plus I epsilon 3, then h2 times this is epsilon 2 I 4. Okay. So then what I will write in place of h1 plus is2, I will write h. So this is h by h, it can cancel out, then it can add this is ux at xy. Similarly, minus I, and this is h1 plus is2 is your h, so h by h, this will be 1, so this will be I times, this is uy at xy, this is h1 by h, this is epsilon 1 plus I epsilon 3, then plus s2 divided by h, and this is epsilon 2 plus epsilon 4. Okay, so what we got here, what is the we know h is your h1 is2, so whatever will be your h1 by h, so obviously modulus of this one is less than 1, and similarly s2 by s modulus will be also less than 1. So what can I write? h1 s modulus is less than equal to 1. Okay, so if s2 equal to 0, then this thing will be equal also. So since h1 by h is less than equal to 1, then h1 by h whole into epsilon 1 plus I times epsilon 3, this thing tends to 0, h tends to 0. Also s2 by h, this thing value is less than equal to 1, so s2 by h whole into this epsilon, this epsilon 2 times epsilon by 4, this thing goes to 0, h goes to 0. So what we will get? At limit h goes to 0, f of plus s minus f of z divided by, so limit goes to 0, so after applying limit h goes to 0, these two things will cancel out. Okay, this thing I have written here, so only this thing will left, so this will be your ux at x minus I times uy, hence f is differentiable because limit s goes to 0, this value is your this one we already got here, hence we can say f is differentiable, hence f of z is differentiable. So what we got here in the sufficient part, okay, this is proved now. So what we got in the sufficient part, so previously we know that a function, or what you can say, when you can say f of z is differentiable, when f of z differentiable at z, so it will satisfy two conditions. First, C-REquations at z must satisfy, C-REquations at z must satisfy, what you got here, the ux, okay, I will write u, then v, then ux, uy, vx, vy are continuous at z, that means they are continuous at xy. So if these two conditions will satisfy, then you will say, if these two conditions are satisfied at a point z, then you will say that f of z is differentiable at z. So this is the sufficient condition. This only this condition is not sufficient. If we will add this second condition, then it will be a sufficient condition for the differentiability of a function f of z at a point z. Okay. Okay. Today's class is only this much. Thank you.